All right, so we're recording, and as I said, the first thing we're going to do today is go through the quiz solution. So let's start with the first problem. In this problem, we have a train that's accelerating basically from rest to 55 miles per hour. And it takes 25 seconds to undergo this acceleration. So based on that, we want to find what the acceleration A is equal to. So we're going to use the definition here that I gave you, A equals delta V over delta T. But look at the problem. We want this to come out in meters per second squared. So the speed of 55 miles per hour has to be converted first to meters per second. So to be clear, delta V is 55 miles per hour. That's our final velocity, minus 0 as our initial velocity. That's how we want to think about the change, delta V. So now let's do some unit conversions. So we want the time unit on the bottom here to be seconds, not hours. So in every 1 hour, how many seconds do I have?
3,600.
Yeah, 3,600. It's just 60 times 60, right? So I'm just going to do that in one step. And then we cancel out hours. But now we have miles as our distance unit, whereas we want that to be meters. So for this, we're going to use the conversion that's given to us in the problem. Okay, which is for every 1 mile, I have 1,609 meters. So now I can cancel out miles, and now I get something in meters per second. So my change in velocity is in meters per second. I just need to do 55 times 1,609 over 3,600. What does that work out to, everybody?
25.
It's about 25, yeah. So that means if I plug in that delta V of 25 meters per second, that's my change in velocity. If it takes 25 seconds, delta T, to undergo that change, this is the ratio. So it comes out to a nice clean number of about 1, if you round off to 2 sig figs, meters per second squared. Okay? So that would be our answer to the first question. Second question is in 2 parts. We drop a ball from the top of a 70-meter tall tower, and we just let it fall to the ground. So let's start with a picture of what's going on here. Okay, we're going to keep track of where this ball is at any moment in time using a y-axis. The typical thing to do is set y equals 0 to be ground level. So that means up here, the height y is equal to 70 meters. So this is what the ball looks like starting off. It's up here at the top of the tower at y equals 70 meters. And what can I say about its initial velocity? That's v naught y. It's equal to 0. So the word that's tipping me off to that is dropped right there. Okay? So we drop it, we don't give it any initial velocity. So the kinematic equation I'm going to use here is y equals y naught plus v naught y times time minus 1/2 gt squared. So let's just see what goes into each one of these variables. Y represents our final position. That's when we hit the ground. That would be 0. Y naught is our initial. That's 70 meters of height. And then, as we said, v naught is going to be 0, so that second term in the equation is 0. And then I have minus 1/2. I'll plug in 9.8 meters per second squared for g. And then I'm just left with a t squared right there. Okay? So that's the time we want to solve for. I'm not going to go through the algebra. It's pretty straightforward. But what happens when you solve for t? What do you get?
3.7.
I was getting something like 3.78 actually. Do we agree? So you can work this out and you'll see you'll get 3.78 seconds. So that's the time it takes to fall to the ground. Okay, the last thing here is how fast is it moving at the moment when it hits the ground. For this one, we can use the following kinematic equation. We can say Vy equals V naught y minus gt. And then we can simply plug in the time that we found earlier to get our final velocity. Okay? our initial velocity is still 0, so that goes in there. And then I have minus 9.8 meters per second squared, and then multiply by t, 3.78 seconds. And what does that work out to? Yeah, it's minus 37 meters per second. And that negative sign is only telling us that we're moving downwards. So if we were to indicate a speed, we would just take the absolute value of that, which is 37 meters per second. Okay? Any questions on this? Okay, so hopefully that's pretty straightforward. Again, I'll post the solution. You'll see it on campus. Okay, so we're going back to our kinematics in 2 dimensions lecture. And the next topic that we want to hit on is projectile motion. So we've already set the stage for how to deal with projectile motion. It's really just a special case of those kinematic equations that involve vectors that I showed you earlier on Tuesday. So let's get into this. So first of all, what do we mean by projectile motion? Projectile motion is the motion of anything that is launched into the air in some way. So it can be thrown at any angle. We're not just dealing with one-dimensional motion anymore. Okay, so back in chapter 3, when we were just dealing with one-dimensional motion, we assumed that if an object was in free fall, it's just moving on a straight vertical line. Okay, now I want to allow for the idea that it could be moving in 2 dimensions, so I can launch it into the air at any angle like this. It's going to be moving in a 2-dimensional path. So we'll have a vertical motion, which we typically call y, and a horizontal motion, which we typically call x. Okay, let's just establish some of the assumptions we're making here before we write down the equation. The first assumption we'll make is that whatever our projectile is, it's moving over a pretty short distance compared to the size of the Earth. Okay, so we're not talking about launching a missile halfway around the globe. That's not going to be what we're dealing with. We're just dealing with short distances compared to the size of the Earth. So that way, the curvature of the Earth can be pretty much neglected. That's the reason for that. Also, as we'll find out in later chapters, the fact that we're on a rotating Earth has subtle effects on how projectiles move. That's pretty complicated to deal with, so we're going to ignore those effects, which is okay because they happen to be pretty small under most circumstances. And as usual, we're ignoring air resistance. Okay, so in other words, we're just assuming that Earth's gravity is the only relevant influence on the object's motion, no other effects. So if that's the case, we can treat projectiles as objects that have a constant acceleration as they move in 2 dimensions. And that's something we know how to deal with based on what we set up on Tuesday, okay? So let me show you how to write down the kinematic equations for a projectile, and then we'll go through some examples about how to use these. So as I said earlier, the standard way to set up your coordinates is like this. You have the x-axis corresponding to the horizontal direction, and then you have the y-axis pointing straight up, corresponding to the vertical direction. So we know what the acceleration of a projectile should be. Okay, we've already seen this number before, but I just want to remind you it's 9.8 meters per second squared downwards. So if we want to write this acceleration as a vector, here's how we would do that. We would say A is equal to 0 times I hat. What does that mean? Gravity doesn't accelerate things in the horizontal direction. It just doesn't do that. It accelerates things just in the vertical direction. And the acceleration in the vertical direction is negative if we're saying, positive y is up, right? If our acceleration is down, we want to put a negative sign. And then we say minus g times j hat. Where we remember g is this number, 9.8 meters per second squared. In other words, when we refer to g, we're talking about the magnitude of the acceleration. If I want to show it's pointing down, I'll write the vector like this, okay? So remember last time we had these 2 vector kinematic equations that we were introduced to. The first one says r equals r naught plus v naught t plus 1/2 at squared. Remember this? we also remember that for each one of these vector kinematic equations, we can actually write a separate equation for the x and the y motions. Okay, so that's what we're going to do here. So for the x motion, now my final position is x, my initial position is x naught, my initial velocity is v naught x, so I'm just picking out the x component of that velocity, times t, but check this out. In the x direction, we don't have any acceleration, right? So I don't have a third term that goes right here, okay? For the y motion, final y position, calling that y, initial y position, calling that y naught, so that goes in here. Initial y velocity, v naught y times time, and then what's our acceleration in the y direction? It's minus g. So this last term becomes minus 1/2 gt squared. So what do these equations tell us? They tell us what the x and the y positions of a projectile will be at any moment in time. So if you know how the projectile was launched into the air, you know what starting velocity it had, and you know where it started off, you can predict where it's going to be anytime later. That's what this is for. You can also predict the velocity at any time later. Because remember this equation, it says v equals v naught plus at as vectors. So if we just pick out the x component for this equation, this says vx equals v naught x, but then remember our acceleration in the x direction is just 0, okay? And then for our y, we have vy equals v naught y minus g is our acceleration, so we have minus gt. So take a look at this one real quick. What this is essentially saying is that your velocity for a projectile in the x direction is just whatever velocity you start with. In other words, it just stays constant over time because gravity doesn't accelerate things in the x direction. It doesn't change your x velocity. It only changes your y velocity. Okay? Make sense? So those are the equations. Let's talk a little bit about the initial velocity because this is something that comes up a lot in problems. Most often, the way you're going to be given information about the initial velocity of a projectile is in polar form. So in other words, I could tell you that a projectile is launched at a certain speed and it's launched at a certain angle as well. If you watch baseball, this is something they commonly broadcast during the games, right? The launch angle when someone hits a baseball and the launch speed as well. So when we talk about the initial velocity, this is really important to remember. That is the velocity your projectile has after it's launched into the air, okay? So, for example, let's say I'm throwing something. Let's say I'm throwing a ball to you. When the ball is in my hand and I'm pushing it forward, it's not a projectile yet because gravity is not the only thing influencing its motion. I'm pushing it with my hand, correct? It's only the moment it leaves my hand that it becomes a projectile, and then we can start using our projectile motion equations. So in that example, the initial velocity would be the velocity of the ball at the moment it stops touching my hand, at the moment I release it, okay? And you can think of other examples, like a cannonball or something, right? It's the moment it leaves the cannon. That's when we have some initial velocity, okay? So just to be clear. All right, so most commonly, you're going to be given an initial speed, v naught, and then a launch angle, which we'll call theta naught. So this is what you should be picturing. This is your initial velocity vector. It's showing you exactly how the projectile is moving at the moment it's launched. And it can be oriented at any angle, right? If it was, let's say, at 90 degrees, that would mean we're launching the projectile straight into the air, right? If it were oriented at 0 degrees, that means we'd be just firing it off horizontally like this. So any angle is possible. Hopefully that's clear, right? So remember, if we have the initial speed and the launch angle, that's the vector in polar form, we can easily take that into Cartesian form, where instead we look at the components, right? So I'm just going to label those components for you on the diagram. This is v naught x, So it's the projection of our vector onto the x-axis. And this is v naught y. It's our projection onto the y-axis. So just remember how this works. If I want v naught x, I'm going to take v naught times cosine of theta. And if I want v naught y, I'm going to take v naught times sine of theta. So this is just how we transform into Cartesian. If we wanted to go the other way, right? If we had x and y components and then we wanted a speed and an angle, here's how we would do it. The speed, v naught, is given by the square root of v naught x squared plus v naught y squared. So hopefully these are looking familiar. These are just the standard way we transform vectors. And then tangent of the angle would be v naught y over v naught x. So we could use that to calculate what the angle is if we had the x and y components. Okay? So do we have any questions on this, how this works? I'm basically just applying what we know about vectors in general to this initial velocity. Okay? So with that said, I think we have enough information to do an example. Okay? I think the examples are going to help. So here's what's going on. You are standing at the edge of a cliff, which is overlooking a large flat valley floor. The valley floor is 300 meters below you. You fire a cannonball over the valley with an initial speed of 200 meters per second at an angle of 40 degrees above the horizontal. Okay, so imagine taking our cannon, pointing it up at 40 degrees, and then firing the cannonball off at 200 meters per second. And we're doing this from a pretty large height, right? So it's going to fall down to the valley floor below. So a couple questions here. The first one is, how far from the base of the cliff does the cannonball land? So how many meters away from the base of the cliff do we land? What is the cannonball's speed just before it hits the ground? We're going to calculate that. So it comes out of the cannon at 200 meters per second, but just before it hits the ground, it's going to be moving at some other speed. We'll figure that out. And then in what direction is it moving just before it hits the ground? We'll work that out too. And then the last question here is, what is the maximum height that our cannonball reaches above the valley floor? So those are a lot of questions. We'll go through each one of those systematically. And we're going to start by drawing a picture, right? The very first thing we should be thinking is, we have all this text, let's put a picture down on the page so we can just visualize what's going on, okay? So we'll start there. All right, so the picture that I have in mind here is this. We have the cliff, and then we have the valley floor below. That shows the situation right there. And the idea is we start right here at the edge of the cliff. We fire off the cannonball. Goes up, but comes back down at some point. And then it lands over here somewhere. Okay? So let's set up an XY coordinate system to keep track of the motion of this cannonball. Like I said, the typical thing to do is to put the y-axis going up like this, and the x-axis going horizontally like this. So that's what we have. Okay, so if you notice, the origin of my coordinate system is right there at the base of the cliff. So I'm going to put a little symbol O for origin. Okay? So what is the starting position of my projectile? That would be x naught, y naught. What is the starting position?
0, 300.
Yeah, so my x coordinate up here is 0, because it's just above the origin. But the y coordinate is 300 meters. Is that clear? So that would be my starting position, which is given by the x and y coordinates. What about down here? Now remember, the way I write my final position is just to say x, y, without the subscript 0. Okay? That's how this works. So, do I know my final x position? Do I know, in other words, how far along the x-axis I am from the base? Do I know the value of x? I don't think so. That's what I'm trying to figure out, right? So I'm going to put a little question mark for that one. But do I know my final y position? that would be 0, right? Because we're setting y equals 0 to be at ground level, just in the way we set up our coordinates. Does that make sense? Okay, let's do some other work. Let's calculate what the initial x velocity is. That's v naught x. We're going to just use this later in our equation, so I'm just going to do it at the outset. Remember, this is given by v naught cosine theta naught. So in other words, if I want to know my initial velocity along the x direction, that's going to be the initial speed, which is 200 meters per second, times cosine of my launch angle, which is 40 degrees. So can someone work out for me what that is? 200 cosine of 40 degrees. And while you're doing that, let's write down v naught y equals v naught times sine of theta naught. And what I'm putting in for that is 200 meters per second times sine of 40 degrees, okay? Is that clear? So what are we getting for v naught x?
153.
153, and so we keep 3 sig figs on that, but what I'm going to do is just put a little bar above the 3, and then add the last digit as 0.2, but we know eventually we're going to round off to 3 meters per second. What about for v naught y?
128.5.
128, I'm getting 128.6 meters per second. Okay? So that's how fast we're moving along the x-axis to start off. That's how fast we're moving along the y-axis to start off. That's how you want to think about these two velocities, okay? All right, so the other thing involves time. Let's bring that into play. So this is the point where we launch the projectile, right? It's up here. That launch happens at t equals 0. This over here is where we land. And we don't know the time of landing. And that's what we want to figure out to start, okay? The first thing we're going to do is figure out how long it takes to land. That's going to be a very useful piece of information that we're going to use throughout the rest of our calculations, okay? So here's how I'm going to go about doing that. I'm going to write down my y equation for this projectile. It says y equals y naught plus v naught y times time minus 1/2 gt squared, okay? Now let's think about what we're putting in here. My final y position, we already wrote it down on the page, but what goes in there? 0, right? Initial y position, what goes in there? 300 meters. Okay, initial y velocity. We had to do a little bit of work to get that, but there it is. That's what we got when we resolved it into components. So that's 128.6, right? Meters per second. That multiplies t, which we don't know, trying to find t, minus 1/2 g is 9.8 meters per second squared, and that's multiplying t squared. So that's a nice quadratic expression, right? Let's just review how this is going to work. This term right here in front of t squared, in the quadratic formula, what do we call that?
A.
That's the a term. This is the b term, right? This is the c term. So I'm not going to go through the whole thing. I'm just going to say that that's a, b, and c. And you can plug that into the quadratic formula, which is given by t equals minus b plus or minus the square root b squared minus 4ac over 2a. So just plug these values into this formula, and here's what you'll get, okay? You'll get one solution is minus 2.16 seconds. The other solution is 28.4 seconds. Now, which one of those is the one I actually want?
28.1.
Yeah, so of course, we want a positive time. It takes 28.4 seconds of flying through the air before this thing lands. Does So that's the correct one. This one's incorrect. Okay. Now remember, the question we're answering is how far from the base of the cliff does this cannonball land? That's x. Okay, that's my final x position. So there's a kinematic equation that directly gives me that. It goes like x equals x naught plus v naught x times time. Okay? So again, we started with the y equation. We used that to solve for the time. Now we're using the x equation. And for this, we can just directly plug in the values. X naught is 0. V naught x is up here. It's 153.2 meters per second. And then the time in which we land is 28.4 seconds. Can someone just crunch those numbers? 153.2 plus, times 28.4?
4,351.
4,350 meters. That is correct. So this travels, a couple miles basically before hitting the ground. But it has such an immense initial speed that that's going to be possible. Okay? So any questions on how we got this? That's the first question. The second question has to do with speed. How fast is this thing moving at the moment when it hits the ground? Well, for that, I'm going to use my velocity kinematic equations, which I'll just write down real quick for you, okay? We just showed that for a projectile, Vx, the velocity as it's moving through the air, is just v naught x, and that's it. So whatever velocity you started with in the x direction, you're just going to maintain that because gravity is not changing your velocity in the x direction. So that's going to be 153.2 meters per second. Okay? For our y velocity, we're going to have v naught y minus gt. That's the equation. We can just directly plug in the known values into this, okay? So for v naught y, we had, it's up here, 128.6 meters per second. Then I'm going to subtract 9.8 meters per second squared, that's g. And then I'm going to plug in this value of time, 28.4 seconds, okay? Can someone work that out for me?
Negative 149.7.
Negative 149.7 meters per second. Now, does it make sense that this came out negative? What is that telling us? Yeah, we're going down. And of course, you'd have to have a negative y velocity if you're on your way down and just about to hit the ground, right? So if this came out positive, that would tell us we did something wrong. But it makes sense it came out negative, okay? All right, great. So we have the x and y components of the velocity of this thing at the moment just before it hits the ground, okay? Which means we can find the speed. Speed is nothing more than the magnitude of the velocity. So the magnitude of the velocity is the square root of vx squared plus vy squared, okay? So we'll plug in the numbers. We have square root 153.2 meters per second, square that, plus negative 149.7 meters per second, square that as well. Okay, now this comes out to 214 meters per second. So that's the speed of this projectile on impact with the ground. Okay? Does anyone know how to find the angle? So we were asked not only, what is the speed just before hitting the ground, but what direction is it moving in? We could give that with an angle. Let me explain how that would work. If I said we're moving at 0 degrees, that means we're just moving straight along the x-axis, right? If I said we're moving at, positive 45 degrees, that means we're moving in this direction. So an angle would tell us which way we're moving. How do I get that angle? Yeah, it's just tangent, right? Here we go. So tangent of the angle I'm looking for is Vy over Vx. And the angle I'm looking for, therefore, is the inverse tangent of Vy over Vx. Let's just do it real quick. So if you crunch these numbers, here's what this will work out to. Negative 44.3 degrees. And technically that's in the fourth quadrant. You could add 360 to that to make it a positive angle, as we saw before. But this is an equally valid way of saying it. This just means we're going below the horizontal for our angle. So to draw it out, our velocity vector at the moment of impact is pointing like this, 44.3 degrees below the horizontal. That's what that negative sign is indicating. Okay? Any questions on that? All right, so there's one last bit, which is to find out the maximum height. So let's actually go back to this diagram. So we're launched from this point. We move up for a while, and then we start to move down, and then we hit the ground. What we're asked for is how high above the valley floor is the peak of the motion, okay? So let's really think about how that's going to be calculated. So I want to know how high this thing is off the ground at the moment it reaches its peak. So remember, the velocity is always tangent to our trajectory. So if I were to draw the velocity of the object at the moment it reaches its peak, it's actually just going completely horizontal. Does that make sense what I just said? It's going completely in the positive x direction. And that means its y velocity at the peak is equal to 0. That's true of any projectile. When it reaches a peak, it's moving completely horizontally for that moment, which means its y velocity has got to be 0. Okay? So we're going to use that fact to make the calculation. Okay, so at the peak of the motion, we have Vy equals 0. That's great. One of the kinematic equations we can use is this. Vy squared equals V naught y squared minus 2g times y minus y naught. Okay, hopefully that one looks familiar. So I'm just going to plug in exactly everything we know. Okay, we're saying the final velocity in the y direction is 0, right? So that means I put in 0 right there on the left side. My initial velocity in the y direction, this is at the moment when we launch the thing, is what we found earlier, 128.6. We worked that out before, right? Okay, but I square that in this equation, and then I have minus 2 times 9.8 meters per second squared, and then check this out. I have y minus y naught. What I'm trying to find is y. That's the height of my projectile at the moment when we reach the peak. So that's just a variable. But y naught is 300 meters. That's the starting height. Okay, so just to be clear about what I'm doing here, for this last part, I'm just thinking about the motion starting from this point and then ending at the peak. So I'm just thinking about this segment of the overall motion. When we do that, this is what our equation looks like. So in the interest of saving some time, I'm just going to give you what y comes out to. Some simple algebra to solve for y. It's 1,140 meters above the valley floor. So the really important piece of information, again, is that at the peak, we can set Vy equal to 0. All right, so we used pretty much all the kinematic equations in this example. Hopefully you see how problems like this work. Do you have any questions? So now that you've seen some examples, Let's ask a few conceptual questions to check our understanding. So I have two objects. I have a blue ball, which is dropped from the top of a very tall building. It falls straight down. And at the exact same moment that I dropped this one, I throw this red ball so that it's moving just horizontally at the moment when I release it. Okay? So these are the two paths that we're thinking about. Of course, what we're going to do is ignore air resistance. So just think about the influence of gravity on the motion of these two objects. What statement is true? Which one of these is going to hit the ground first? Is it going to be the blue ball hits the ground first? Is it the red ball hits the ground first? Or is it true that they'll just hit the ground at the same exact time? So I just want to know where your intuition is at on this one. Don't try to calculate anything. What do you think the answer is? Who thinks the answer is A? If we release these two objects at the same time, this one hits the ground first. So I got a few people saying it's the blue one. Who says it's the red one? Okay, who says they hit the ground at the exact same time? Okay, you're correct if you said they hit the ground at the exact same time. Now, I'm going to show you exactly why this works out using equations. But the idea behind what I'm about to show you is that the x motion and the y motion of a projectile are totally independent of each other. Now these two projectiles obviously differ in terms of their x motions, right? But in terms of their y motions, it's exactly the same thing. This one starts off with no velocity in the y direction. And so does the red one, in fact. So for that reason, they start with the same y velocity, they start from the same y position. It should take them the same exact amount of time to hit the ground, because their y motions are identical. So let's kind of flesh that out in a little more detail. So the idea here is for both, the initial y velocity is equal to 0. So that's, of course, true if I just drop something. It's also true if I throw something horizontally. It's not moving in the y direction to start off. Okay? And also for both, there's some kind of initial height, which I'll just call h. So h is just whatever the height of that building is. Okay? And then they both hit the ground, so they both reach the same final height. So for both of them, we start off with no y velocity at some height h, and then end up at some height 0. So that's the same for both. So let's see what goes on there. If I plug in all of that to this kinematic equation, which I'll write down as y equals y naught plus v naught y times time minus a half gt squared. Okay, for my final y, I get 0. For my initial y, that's h. For my initial velocity in the y direction, that's also 0 for both of these. And then I have a half gt squared. So I have then a half gt squared equals h. And then t, the time it takes to hit the ground, if we just solve for it here, be 2h divided by g under the square root. And this, of course, is the same for both. Okay, so in this situation, they take the same amount of time to hit the ground. Would that change if I threw the red ball up at some angle? Yeah, in that case, they wouldn't take the same amount of time to hit the ground. Or if I threw it straight down or something like that. But as long as I'm releasing the red ball horizontally, this holds true. Okay? And actually, I'm going to show you. Oh, wait, that's the wrong thing. So I'm going to show you a video. I actually stole this from Harvard. I'm going to do this from time to time. This is called the shoot and drop experiment. It's exactly what I described in the problem. Okay, one ball is just going to be dropped, and the other one's going to be fired horizontally, and you'll see that they hit the ground at the same time. So let's watch. Okay, so hopefully you're convinced by the equations and by the actual video. Okay? You can take a look at the link to this video, by the way, if you go to the lecture slides. Okay, so here's a variation on that same question. We have a blue ball dropped from the top of a tall building at the exact same time. This red ball is thrown horizontally. So this question has to do with which one is moving faster upon hitting the ground. Is the blue one moving faster? Is the red one moving faster? Or are they going to hit the ground moving at the same exact speed? Let's just put this one to a vote. Just give me your initial thoughts. Okay, who says it's A? This one, the blue one's going to be moving faster when it hits the ground. Who says it's B? Red ball. And then who says it's C? They hit the ground at the same speed. So in this case, the answer is B. It's the red ball that's going to have the greater speed upon hitting the ground. So you might have some intuition for this already, but what I want to show you is how can we make our equations kind of pop this answer up for us, okay? Without plugging in any specific numbers. Okay, so let's think about this. For each one of these objects, we're going to have an x velocity and we're going to have a y velocity. And the speed is just the square root of vx squared plus vy squared. So if I'm asking a question about the speed, I need to know both the x and y velocity of the object when it hits the ground. Okay? So for my x velocity, that's just v naught x. Whatever x velocity I end up with is the same x velocity that I start with. That's what we found in our kinematic equations. But okay, for the blue ball, the one I just dropped, what's the initial x velocity?
0.
It's just 0. So I'll say that this particular value is equal to 0 for the blue ball. But for the red ball, is this equal to 0? No, the red ball hits the ground and it does have some x velocity. We don't know what it is, but I'll just say it's something greater than 0 for the red ball, okay? Okay, what about for our y velocity? This is given by the kinematic equation. Vy equals v naught y minus gt. Okay? Now for both of these, remember the initial y velocity is 0. And for both of these, it takes the same amount of time t to hit the ground. So this y velocity upon hitting the ground will be the same for both. So they end up hitting the ground with the same y velocity, but the red one has a bigger x velocity. So that means the red one is moving faster overall. Do you see that? So that's how we can get this to come out of our equations. All right, any questions on these last couple conceptual examples? Okay, we'll keep it moving then. Okay, I have another conceptual example for you. So I'm first going to tell it to you in words, and then I'm going to show you an animation. Okay, so this is kind of a classic physics problem. You see it in pretty much every textbook. You may have seen this if you've taken like high school physics before. So here's what's going on. A wildlife biologist sees a monkey hanging from a tree branch, and he wants to hit the monkey with a tranquilizer dart in order to capture it. At the moment that the dart is launched, the monkey is going to let go of the tree branch. Okay, so we have this dart which is fired, and then we have the monkey which lets go of the tree branch. And both of those motions just happen at the same exact time. Okay? So, of course, the goal is to hit the monkey with the dart. So, how should the biologist be aiming the dart in order to achieve this? Should the biologist be aiming a little bit above the monkey so that by the time the dart gets to the monkey, it hits it? Should the biologist aim a little bit below or directly at the monkey? Or do we need some more information to really answer this? You can cross off answer D. It's one of these three. So what do we think? Do we want to aim a little bit high, aim a little bit low, or just like right at the monkey to achieve this?
Below.
Who says it's A? Who says we want to aim a little bit high? What about aiming a little bit low? Okay. What about just aiming directly at the monkey? Yeah, so if you answered C, you're correct. So I want to show you why this is the case, all right? So first, let me show you an animation to help you visualize this, okay? So there's the biologist, I'm just gonna show the dart as a blue dot. And again, at the moment when that thing is launched, the monkey lets go of the branch. So how can we say that the dart hits the monkey? Well, remember how this works when we have a collision or one object meeting another object? We set their positions equal to each other. So if I were to come up with some kind of kinematic equation that gives me the position of the dart, which I'll call RD, so R is for position and D is for dart, I want to set that equal to RM. That's what ensures that we hit the monkey, right? And if I do this and just kind of see what comes out, that should tell me how I need to aim in order to hit the monkey, okay? But here's the animation. All right, so we want that to happen. All right, make sense? Last detail, I'm going to work this out for you on paper. The last detail is for our coordinate system. I'm just going to put the origin right here where the dart begins its motion, okay? So let's work it out. Okay, so, you know, there's many ways you could go about doing this. I'm going to show you the most efficient way. What I'm going to do is apply the following kinematic equation for position. And I'm going to do it in vector form. So this says R equals R naught plus V naught times T plus 1/2 AT squared, where position, velocity, and acceleration are all expressed as vectors, okay? And what I'm going to do is separately apply this equation to the dart and to the monkey. So let's do it to the dart to start off. Okay, so this says the position of the dart equals, what's my initial position, just the way I set up the problem? So remember, we put the origin right where the dart is initially starting off, so that means its initial position is 0. Okay? Then I'm just going to write V0 for the dart. So this is whatever the initial velocity is. I'm not even going to assume anything about it for the time being. And then we have 1/2 AT squared. So this is the acceleration from gravity, but I'm just going to write it this way for now, okay? What about for the monkey? So if the dart starts off at the origin, the monkey doesn't, right? The monkey has some initial position, which, again, I don't want to say anything too specific. I'll just say this is initial position for the monkey, R0M. But what can we say about the initial velocity for the monkey? It's 0. The dart has some non-zero initial velocity, of course, but the monkey just lets go of the branch, so it has 0 initial velocity. And then I'll put 1/2 AT squared for the acceleration due to gravity. Okay? Now, if I want to say the dart hits the monkey, then that means I'm setting the position of the dart equal to the position of the monkey. At some moment in time, their positions are equal. Okay? So just set this guy equal to that guy. Set V0D times T plus 1/2 at squared equal to r0m plus a half at squared. So here's the important thing to see. When I set these equal, the acceleration terms just cancel each other out. So in other words, the dart and the monkey are accelerated down by gravity just by the same amount. So they cancel. And here's what we get. The initial velocity of my dart should equal 1 over the time, whatever that happens to be, times the initial position of the monkey. So this answers the question. The initial velocity of the dart should be the same direction, that vector should be in the same direction as the initial position of the monkey. That means we're just pointing right at the monkey, if you think about it. Because if we draw a little picture, right, this is my x and y coordinates, and this is where the monkey is to start off. The initial position vector for my monkey goes straight from the origin to that point, right? And what this is saying is my initial velocity is pointing in the exact same direction. So that means we don't aim high, we don't aim low, we just aim straight towards the monkey. And as long as the two motions start off at the same time, we should hit the monkey. Okay? All right. So let's do some more with this projectile motion stuff. Let's talk about the range of a projectile. So first, let's explain what we mean by range. The range of a projectile is the total horizontal distance that it travels from the moment that it's launched until the moment that it hits the ground. But what we're assuming here, we're going to derive an equation, and we're going to use it in a few examples, but before we even get there, just really be clear on what we're assuming. We're assuming that the initial height and the final height are exactly the same. Okay, so if I'm just like launching something over flat ground and then it lands on the ground at the same height, this equation will work to give you the range. If, let's say, I launch something off a building and then it falls down to a lower height, this equation doesn't work. Okay, so important to keep that in mind. So the equation's up on the slide, but I'm going to show you how it's derived and then we'll go back to it. Okay. So I'm going to start with the y kinematic equation for a projectile. This says y equals y naught plus v naught y times t minus 1/2 gt squared. Okay? Now, what we're assuming is that the initial height y, or initial height y naught, is the same as the final height y. Okay, so we are launched from and we land at the same height. Okay? So that means these two terms just cancel each other out, assuming equal heights. Okay? So then we'll just have 0 equals these two terms added together. But notice how I can pull out a factor of t. So I can write this as 0 equals t times v naught y minus 1/2 g times t. Okay, just factoring out t from the equation we have. So what do I do next? I'm trying to find time. That's what I'm doing for the time being. I'm trying to find how long it takes to land. Okay. Now, I have two different terms multiplied together, which give me 0. Whenever we're in this kind of situation, it means this one could be 0, or the whole thing in parentheses could be 0. One or the other has to be true, right? So one possible solution is just t equals 0. That's not super interesting, right? That just means if you wait no time after the projectile is launched, you're still at the same height you started, right? Okay, that's not the one we want. We want this one, which is how long does it take to come back to that height after the motion has taken us there, okay? So I'm going to say v naught y minus 1/2 gt equals 0 for that one. And then I'm going to solve for t, which if you rearrange this, you can show that it comes out to 2 times v naught y divided by g. So if I launch a projectile and it lands at the same exact height that we started at, this is how long it will take to land. That's what this is. Okay? Okay, so that immediately takes us to the range. Because the range would be how far has it traveled in the x direction during that time. That makes sense? The range is just how far it's traveled horizontally in that time. So for that, I'm going to use my x kinematic equation. That's x equals x naught plus v naught x times t. So now I'm going to call the x distance we travel the range r. Okay, it's a horizontal distance. Now, I'm just going to assume we start at 0 for x naught. And then for v naught x times time, I'm going to sub in the t value that we just found. So I have v naught x times 2, v naught y divided by g. Okay? But let's take a closer look at that. V naught x, if you remember, is your initial velocity times cosine of the angle at which you launch. And v naught y is your initial speed times sine of the angle at which you're launched. Okay? And that's all divided by g. So to put it all together, we have 2. I have v naught squared, and then I have cosine times sine. And then we divide by g. So we're almost done. I just want to write down a trig identity that's going to be used here, okay? If I have 2 times sine times cosine of some angle, you may know this from geometry, that's equal to sine of twice that angle. It's a little more convenient to write it this way just so we don't have 2 different terms floating around, okay? So applying that trig identity gives me v naught squared sine of 2 theta divided by g as the equation for the range, okay? But again, I can't emphasize this enough. We're assuming the heights that you start at and you end at are equal, okay? So there's where the equation comes from. Any questions about how I did that? Yeah.
Is the 2 v naught y over g, is that the hang time of the projectile?
Yeah, so this is the total time in the air. You might call this the time of flight. But again, assuming equal starting and ending heights. Yeah. All right, anything else? So let's take a look at one example where we actually get to use this. So let's say, okay, this is the range equation, we just derived it. Let's use it. A soldier has a cannon that can fire projectiles at 200 meters per second. I'm writing that in scientific notation, but that's just 200 meters per second. We want to hit a target that is 865 meters away. So the question is, what is our angle that we should launch the projectile at in order to do this? Okay, so let's be clear. 865 meters, what variable in this equation is that corresponding to?
That's r.
That's r. We want the range to be 865 meters, right? And what about this right here, 200 meters per second? That's v naught. So we know r and v naught, and we of course know g. So we can solve for theta. That's the idea. So let's go through it. Okay, here we have r equals 865, v naught equals 2 10 to the 2 meters per second, and then g, of course, 9.8 meters per second squared. Put that into the range equation. which says r equals v naught squared times sine of 2 theta divided by g. So we're trying to solve for theta, so we'll rearrange this to say sine of 2 theta equals r times g over v naught squared. We agree? So I have sine of 2 theta equals, let's plug it in, 865 meters, 200 meters per second, and we'll, I'm sorry, that should be g right there, my bad. 9.8 meters per second squared up here, and then divide by v naught squared on the bottom. So we have 200 meters per second, we square that on the bottom. Okay, so basically, try this. Punch in 865 times 9.8 divided by 200 squared. I hope you agree that you get 0.2119. So the equation we're trying to solve is sine of some angle equals 0.2119. So how do we proceed from here? How do I get the angle out?
The inverse thing?
Yeah, I can take the inverse sine. So 2 theta should equal the inverse sine of that number, correct? Okay, so then we'll get 2 theta equals, what does your calculator spit out?
12.23.
Yeah, 12.23 degrees. Now, what I want to tell you is that that is actually not the whole story. That is just one possible answer. There's another one. Okay? So there are actually 2 angles that will work. And I want to show you mathematically why that is the case. All right. Do you all remember the unit circle? Okay. Do you remember that on the unit circle, sine is equal to the y coordinate? So if I draw a unit circle, I'll just draw the top half of it. That's all we'll need, incidentally. So if I'm saying sine of some angle is equal to 0.2, that means the y coordinate on the unit circle is equal to 0.2. 0.2119 to be exact. And what the calculator told us is, well, if I'm at this angle, which is 12.23 degrees, that will work, right? But what the calculator didn't tell you is that if you're at this angle, it will also work. See, because we have the same y coordinate. So this angle goes from the x-axis all the way to here. Can anyone just immediately see what that other angle is? It's basically 180 minus 12.23, okay? Can someone punch that in real quick? What's 180 minus 12.23?
167.76.
Yeah. 167.77 degrees. So here, what I actually have is 2 theta is either 12.23 or it's equal to 167.77. And of course, if I just want theta, I'll just divide both of these answers by 2, okay? So if I take 12.23 divided by 2, 6.12 degrees. That's possible. Or if I take this angle and divide by 2, I get 83.9 degrees. So either one of those could be correct. Let's really think about what that means. If I aim it at this very small angle, what that looks like is something like this. The projectile is shot at a very shallow angle, it spends very little time in the air, and then hits the target over here. At this very large angle, we're really launching it very high into the air, and then it comes down and hits the same point. So actually, both of these angles will work to hit the target like this, and that's why it works out mathematically. So that's it for today. See you in lab if you have Thursday lab.